Hello everyone, I'm Wenfan Song from Zhejiang University. I'm glad to introduce our work, MandiPass, Secure and Usable User Authentication via Earphone IMU. Nowadays, biometric plays an important role in user authentication. For example, fingerprint, facial feature, and brainwave. Traditional biometrics lie into intracorporeal ones and non-intracorporeal ones. The former is secure but hard to collect. The latter is easy to collect but vulnerable to spoofing attacks. Since Earphone will be one of the next computing platforms, an IMU has been integrated into many types of earphones. In this work, we aim to leverage the IMU to collect a brand new intracorporeal biometric to achieve accurate user authentication. However, achieving secure and user-friendly authentication is challenging. First, it is difficult to find a brand new intracorporeal biometric, and theoretically prove that it can be captured by Earphone IMU. Second, raw IMU signals contain much noise, and the sampling rate of IMU is low, which makes the biometric hard to extract from noisy signals. Third, resisting replay attacks remain an open issue for biometric-based authentication. In this work, we overcome the above challenges and propose a system named MandiPass. MandiPass achieves usable and secure authentication by extracting a brand new biometric called mandible print. MandiPass is composed of three modules: data preprocessing, mandible print generation, and similarity calculation. User only needs to produce a voice by his root to generate vibration. MandiPass extracts mandible print from the received vibration signal. I first present the feasibility study and a validation experiment. To confirm that the vibration can propagate from throat to ear, we attached IMU to 3 different locations to the face to observe the vibration strength. The result shows that the vibration is able to propagate along the mandible and finally reach ear. We then built a 1 degree of freedom theoretical model to prove that the received vibration signal contains mandible biometrics. In this model, the vibration can be divided into positive direction 1 and negative direction 1. From the theoretical analysis, we can find that positive direction vibration signal and negative direction vibration signal record different biometrics. Thus, it is feasible to extract mandible print from the vibration signals. Now, I will present how to perform data processing and mandible print generation. In the data preprocessing, MandiPass first detects the beginning of the vibration by utilizing a slight window to calculate the standard deviation. Then, MandiPass leverages MAD algorithm to find all outliers and replace the outliers by the mean of normal values. Next, to eliminate the low-frequency component introduced by body motion, MandiPass filters the signals by a high-pass filter with a cut-off frequency of 20 Hz. Afterwards, MandiPass normalizes the signal values and obtains a feature block with a dimension of 660, where 6 means the 6th axis in the IMU, and 60 means 60 signal values for each axis. To identify users, an intuitive method is to calculate statistical features and use traditional classifiers to identify these features. However, the identification accuracy is not high enough. As mentioned above, positive direction vibration and negative direction vibration contain different biometrics. We thus separate the positive direction vibration signals and negative direction ones by calculating the gradient features. Since convolutional neural network has powerful feature extraction ability, we designed a two-branch feature extractor to extract mandible print from vibration signals. The output of the first fully connected layer is regarded as the mandible print vector. Then, I will introduce the security enhancement part. We first define 4 attack models towards 4 kinds of mainstream attacks. From the analysis, we found that MandiPass can defend against the first 3 kinds of attacks naturally. To defend against replay attacks, MandiPass leverages a Gaussian matrix to transform the mandible print templates to a cancelable one. Once the cancelable template is changed, the replay attacker can't pass the verification. Then, let's move to the evaluation part. We implemented MandiPass on a Raspberry Pi to conduct real-world experiment. We invited 34 volunteers to collect vibration signals. To quantify the authentication performance, we defined 4 metrics: FRR, FAR, VSR, and EER. In the first figure, the identification results show that our feature extractor outperforms other classifiers. The curves of the FAR and the FRR show that the EER is only 1.28%. In the gender and axis experiments, the results show that MandiPass is fair to different genders, and using only 3 axes can achieve sufficiently low EER. In the experiments towards different system settings, the result demonstrates that collecting 60-second training data for the feature extractor is enough. Moreover, the number of the elements of the mandible print vector can be 512. In conclusion, we proposed a novel authentication system, MandiPass, and theoretically prove that the vibration signals affected by the mandible contain mandible print. The experimental results show that the EER of MandiPass is only 1.28%. That's all, thank you. And if there is any question, feel free to contact us.